thank you, Tabby and Yantin and all the organizers. It's my great pleasure to be here. Today, I want to introduce my master student COSAS's recent paper about selecting protoclusters from the Cosmos Web JWST field. Before starting, I want to, in addition to COSAS, I want to thank all the collaborators, all the people in my group, and also Hashimoto-san's group, and other collaborators, including people here. Okay, so let's get started. So why protocluster is important? Well, KJ already covered a lot of them, but I want to remind a few. First point is understanding cluster evolution. If I remind, maybe everybody knows, but the galaxy clusters occupy only less than 1% of the volume of the universe, but in terms of mass content, it's more than a quarter. So it occupies a big fraction of the mass of the universe. Then, if you see a massive cluster monster like this, you wonder what was the progenitor, how did it evolve? And then you want to study for the cluster like this. That's first point. Second point is that to understand galaxy evolution in very dense environment. In galaxy clusters, galaxy density is sometimes 3 orders higher. So galaxy evolution in such a dense environment may be different. Star formation may be morphology different, and also there may be more merger and interaction between galaxies. And there may be a quasar feedback, agent feedback, if there's a massive agent at the center of clusters. So we want to study galaxy evolution in different environments. So this is a metaphor. In a rich environment, like in a Seneca here, and in a poor environment, the galaxy evolution may be different. So we want to see the difference. Okay, and then third, and the other reasons are KG covered, I think, this compare with the simulation models, and then study the galaxy evolution, cosmology, and also there may be a contribution to cosmic reionization if the galaxy number density is 3 orders higher, and then maybe star formation rate is higher in protoclusters. So we're going to study. There are a lot of studies to do with protoclusters, so protoclusters are important. Okay, then I want to look at a little bit of history. So pre-JWST, still, we didn't have very deep near infrared, so we stick to the I-band dropouts from the ground-based telescope. So this is my previous work using the superincome on super telescope, searching for I-band dropouts around the massive quasar aperture 6.4, and we found a protocluster. So there are 7 red galaxies around this quasar. This was, I think, one of the most distant protocluster at the time of this writing. And then later, there came hyperspirancom, so we were able to search much larger volume for protoclusters, but still searching for I-band dropout. This is Hariganes-san found many protoclusters at aperture 6. I helped a little bit on this work. So that was the situation. But then JWST changed the situation. With the JWST NIRCam, we have very deep near-infrared photometry, so we can extend the protocluster searches to redshift 7 and beyond. And then for people, this is very competitive area, so people have found a few protoclusters already. So this one is at redshift 7.6, behind the famous lensing cluster, so 1, 2, 3, maybe 8 galaxies behind the lensing cluster, so that's redshift 7.6. Another example here by Morishita-san at redshift 7.8. This is again also behind the massive lensing cluster, able to 744. This is not a protocluster, but this is a protocluster. You know that, right? Okay. However, as you see, these are individual examples. Still limited number of the protocluster is small. I think the largest one today is this Chen 24 that search protoclusters in Sears field, which is only 100 square per minute. So what we want next is we want the statistical search. We want a large volume. Okay. Then JWST Cosmos Web is suitable for search for protocluster in large volume. Its total area it took almost 2,000 square per minute. So this is 20 times larger than the Sears field. So that's a very good field. So that's why we search for protoclusters with my master student COSAS. So COSAS is a very good student. as soon as database Cosmos Web data is released, he reduced the database Cosmos data by himself. He is fighting with the bugs of the database pipeline, and he was very good at coding. But at this time, only half of the Cosmos data when he started was released. So in this work, we only use half of the Cosmos data. But still, this is 100 times, 10 times larger than CSV. Okay. Then how do we find proto clusters? It's very simple. So we have now near-term very deep in-memory photometry. So we look for F115W dropouts that correspond to redshift greater than 9. And then we connect these dropout galaxies with friend-of-friend algorithm within 2.54 megaparsecs. So if galaxies are within 2.5 megaparsecs, they are considered as friends and then connected to be a group. Within photometric redshift errors. And then select high-density regions greater than 3 sigma. That's very simple. This shows you that, so these are database photometry. Yeah. And then here's so this blue line is F115W. So at redshift of, so in this case, this is redshift 10. It's very faint here. It's a dropout, and then it's bright in 150. So this is basically how we search redshift 9 and 10 galaxies. And then the selection method is already established. This is competitive field. Many people try to select out 115 dropouts. So it's sort of color box, it's already established. So we use this example by Harry Hansen. So if 115 dropouts comes around here. The review of our paper asked us to check if the selection is okay using Jade's spectroscopic galaxies. And then, well, it's not perfect, but most of the redshift 8, 9 galaxies are in this box. So that's good. Then after we select dropouts, we do ASIAA fitting. So this is one example of such galaxy, and it's nothing, and then bright. So that's a typical dropout. And then we fit the SED and then estimate the photo. In this case, 9 points something. Okay. Then we calculate the density using the friend-to-friend algorithm. And then we found 7 protoclusters between redshift 9 and then 11. We selected structures with greater than 3 sigma significance. Something like here. This is between redshift 9 and 10. And here. And this is 10 to 11. And then we found 2 clusters, protoclusters here and here. If we still need spectroscopic confirmation, but if confirmed, these are the most distant protoclusters ever found. I show you some examples. So this is one of the structure with 3.6 sigma, and over density is 9 times over dense than the field average. And then as you can see, these 7 galaxies are close to each other, with photometric redshift probability is something like this. So this is something like 9.5 or so. Another structure here. This is 4 sigma significance with over density of 8. And then again, this one is almost 10 galaxies, around redshift 9.5 or so. Another example, this is 4 sigma with over density of 8. There's 8 galaxies here with again 9.3 or so, redshift 9.2 or so. Last example is this one is 3 sigma, and then over density is 8 times. Again, redshift 9.3 or so. So we find 7 of these structures. Then we look at the. Thank you. So we try to look at the. I think KG said. Thank you very much. The same thing. All these protoclusters need to be connected to the redshift 0 structure. That's what KG said. I'm rather at this side. So this is trying to estimate the halo mass of these protoclusters by adding all the stellar mass of member galaxies, and then using the beta Bellucci, the stellar mass to halo relation. And then, this is a rough estimate, but it comes somewhere around here, 10 to 11 or so. And then the evolution in the simulation goes something like this. So at redshift 0, this is corresponding to 10 to the 15. That's something like a coma cluster mass. Okay. so far so good. But then next step is, as I said earlier, we only use the half of the Cosmos area. And then now we are collaborating with a Type A database team group led by Claude, and Zhengai, TC, and Wei Hao. And then they did a very advanced data reduction of the whole database in Cosmos web data. So in collaboration with them, I'm looking forward to expand the search to the entire Cosmos region. Okay, and also spectroscopic follow-up is also necessary to confirm the structure. Okay, and then paper is just accepted. We're going to post it to Azure page soon, so please pay attention. Okay, I stop here. Thank you very much for listening.
2 more minutes, but thank you. Okay, so questions, yeah.
Tomo, very interesting talk. Did you have a chance to look at the structural properties of those galaxies, the protocluster candidate galaxies?
Oh, structure of galaxies?
Yeah, the morphologies or the Cersei kind of index properties, anything like that?
Not yet, because we are not so confident about member galaxies yet. If I go back here, how do I do that? After I finish. After I finished. Yes, okay, thank you. So we are not so sure about all of these true member galaxies. For example, these members are a little bit voltages offset. So I think spectroscopic confirmation would be nice. And then once we know spectroscopically if they are really protocluster members, then it would be very interesting to look at the structures and properties of these protocluster galaxies.
Okay, thank you.
Thank you for a good question.
Okay, any other question? So the typical number of galaxies associated to each of density is like 4 or 5 at most, right?
Oh, well, in this case, there are 7, yes.
7 galaxies?
Yes.
Okay. But typically, as shown in the map, the number of the galaxies associated to each
Right.
is like 3, 4. So it's a kind of group.
That's true. Yeah,
it
it can be called group.
evolves to a rich cluster.
Right. Yeah. Well, then at this redshift, the number of galaxies is already low, so all the protoclusters, including biggest work, something like that. I found the paper found 2 galaxies and then called it protocluster.
And also, do you see any environmental dependence where, the low density regions tend to cluster more bright galaxies, for example?
That's a very interesting point. We haven't looked into that, but that's definitely interesting.
Right.
Hi, Toma. Thank you for that. I was wondering what the uncertainty is on just the contamination from dusty galaxies, just because it's at higher redshift and you're only using broadband photometry.
Right. Oh, yeah. That's always a concern when you select dropout galaxies. It might be dusty galaxies at low Z. Well, at least these I forgot exact criteria, but I think we throw away that if I think probability density distribution is larger in lower Z, we throw out those galaxies. So that's why our member galaxies all have these very high Z for the Z probability. At least we did that, but yeah, that's a very concern.
Okay, I can take another question. Yes.
Just a very naive question. What's the relationship between delta and sigma?
Oh, the sigma is significant, so we put a random aperture and then see how significant is this structure. And then delta is over density, so compared to average density, how many times density is higher. So it's similar but in different indicators.
Right. But like for the next
example, you have delta lower but with higher sigma.
Right. So because the aperture size and the photo G errors are slightly different in each candidate. So these numbers are slightly different. Thank you.
Okay, let's thank Tomo again.